What I have here is a list of strategies we're going to use. We're going to see these strategies in examples, and it'll help make sense of them all. But some of these strategies we've already seen. So the first strategy, writing the equation using only one trig function and using sine squared plus cos squared equals 1, we've had this on quizzes already, right? You had equations where you had a sine squared and a plus 3 cos x, blah, blah, blah. And you can't solve that because you have two different trig functions. So you learned you could change the sine squared to 1 minus cos squared, and then your function would only have cos, and then you could solve it by factoring or whatever method you needed. So we've seen that a little bit already. What we're adding to it is not only do we sometimes want an equation with only one trig function, like only sine or only cosine, we also want our angles to be the same. So we're going to see sometimes you have a double angle, a 2 theta, and you might want to use one of your double angle formulas to change it to just be a theta. So we'll see some questions like that. We're also going to see sometimes if we have a common factor, we're going to need to factor that out. On your take-home quiz, example number 2 on part 1, and I think there's an example on part 2, they're going to use this strategy. So if you had trouble with that example, today's lesson will help you with that. And a final strategy, sort of similar to identities, is you can sometimes change things to sine and cos. And if you have any fractions, because it's an equation, you can get rid of the fractions by multiplying by something on both sides. So let's look at some examples. Here's our first one. Solve for theta between 0 and 2 pi, where cotangent of theta equals 2 cos of theta. So the first thing we notice in this equation is that we have two different trig functions. So I would look and say, is there a way that I can change cos to cotangent or cotangent just to cos? No, there's nothing that directly does that. So maybe you think, well, maybe I'll try changing cotangent to cos over sine. Now that doesn't change things to just one trig function. So we're kind of using this last strategy that's still listed here, changing things to sine and cos. As part of that strategy, it says eliminate any fractions. You see we have a fraction here. It's divided by sine theta. How would I get rid of dividing by sine theta? Multiply by sine theta. So if I multiply this side by sine theta and this side by sine theta, well, these sine thetas here would simplify, and my equation would just become cos of theta equals 2 cos of theta sine of theta. We still don't have only one trig function. Here, you might be tempted to change sine theta to 1 minus cos theta, because you know sine squared theta is 1 minus cos squared theta. But you're not allowed to change just cos to 1 minus sine, or just sine to 1 minus cos. The only time you can use those equations, sine squared plus cos squared equals 1, and interchange them, is if you have something squared. Otherwise, it doesn't work. So we're not allowed to change that sine theta to 1 minus cos theta. So this one, we've changed to sine and cos. We got rid of the fractions. This is one of the examples where you have to factor. And if you're going to factor something, you need to make one side equal to 0. So I'm going to move the cos theta over to the other side by subtracting. And in both of those terms, we have a common factor. There's a cos theta in both of them. So because there's a cos theta in both of them, we can factor that cos theta out, leaving us with 2 sine theta in the first term minus 1 in our second term. And what that factoring does, that factoring separates these two equations, and so you do get your trig functions by themselves. Now I want to point out another thing that might be tempting for you at this step right here. and some of you have already done this on your take-home quiz. You looked at this equation and said, if I only want to get one trig function by itself, why can't I just divide by cos theta on both sides? Wow. And that would cancel this out, and then I'd only have one trig function. Why doesn't that work? Okay. Well, it is. If I divided this whole side by cos theta and this whole side by cos theta, then these would go away and these would go away. Right? But they appear to not go away for long enough. It may be 0. Can you see at this point right here that if cos of theta is 0, my left-hand side of my equation would be 0. And if cos of theta were 0, my right-hand side would be 2 times 0 times sine theta, which is 0. Last time I checked, 0 was equal to 0. Okay? And so cos of theta equals 0 is one of our options. So if, and this is maybe why everything is disappearing on me, every time I try to divide by cos theta, Smartboard knows that you might be dividing by 0, and it's not allowing me to do this. Or I'm just using invisible ink, right? For the rest of today's lesson, I'm going to use my white pen. Good luck. Okay? So we have to factor instead of dividing, because if we divide by cos, we'll still get this side, that sine theta equals 1/2, but you'll lose all of these solutions. So where is cos theta equal to 0? That's when theta equals, oh, I am using white. Okay, here we go. That's when theta is equal to pi over 2 and 3 pi over 2. And sine of theta equals 1/2. That's when theta is equal to pi over 6 in quadrant 1 and 5 pi over 6 in quadrant 2. Excellent. So you'll notice this in your take-home quiz as well, that sometimes you'll want to divide to cancel things out, but instead you need to factor, because then you will get all of the answers instead of just half of the answers. Okay, our next examples are pointing out, now that we have double angle formulas, sometimes in trig equations you will recognize them and do multi-revolution questions, and sometimes you'll have to use your double angle identities to solve them. So how do we know which one to use? Well, I've got two examples of here, one where you can use your multi-revolution strategy, one where you can use your double angle identity, and what's the difference between them. So I'll let you copy this down before we start this example. The multi-revolution questions that we've done in the past have had a 2x, a 3x, something inside. There has always been a way that you can get that function by itself. So example here, you can get cos 2x by itself. It's equal to positive root 3 over 2. So whenever you have only the trig function with the double angle, then you could solve it as a multi-revolution question. How do we solve multi-revolution questions? What's the first thing we would do?
If cos of x is 0,
Yeah, we would.
then cos of 2x is 0 to 4 pi.
We would first look at our domain. If x is between 0 and 2 pi, then 2x's would be double that. That would be between 0 and 4 pi. You would solve for 2x. When is cos equal to root 3 over 2? Pi over 6. Quadrant 1 and quadrant 4, 11 pi over 6. And that would be 1 time around the circle. But 2x is 2 times around the circle. So in the second time around, now how do we find 13 pi over 6? Well, from here to here, we're adding 2 pi, and 2 pi is equal to 12 pi over 6. So we're adding 12 pi over 6 to this one. Same thing with the 11 pi over 6. If I add 12 pi over 6 to that one, I'll get to 23 pi over 6. If those are the answers for 2x and we're asked to solve for x, then x is pi over 12, 11 pi over 12, 13 pi over 12, and 23 pi over 12. And sure enough, all four of our answers are between 0 and 2 pi, like we wanted to solve from the beginning. So we use our multi-revolution strategy if the only trig function we have is a double angle, so that we could get that double angle cos 2x by itself on one side of the equation with no other trig functions. However, when you have your double angle and another trig function, like the second example with a sine 2x and a sine x, then you have to use one of your double angle formulas in order to solve it. So with sine 2x, I only have one option. I have to change this to 2 sine x cos x. And once again, we have our equation. It's in sine and cos, but we can't change it to all sine. So then we're going to think about our factoring strategy. Move everything over to one side. So subtract that sine x on both sides. And we have a common factor of sine x on both sides. Now that we've done that, sure enough, sine x could be 0. Cos x could be a half. When is x equal to 0? Sine x equal to 0 when x is 0 pi and 2 pi. When is cos x equal to a half? Pi over 3 family, quadrant 1 and quadrant 4. We didn't do this in the last question, but we should always do this. Check your domain at the end, especially when you get answers that are 0 and 2 pi, because I want to make sure that 0 and 2 pi were included. Yes, they were. Can you see how it's 0 is less than or equal to x, less than or equal to 2 pi? So that means both 0 and 2 pi can stay in our answer. Sometimes in your textbook in particular, sometimes they don't include one of those ones, so you have to be careful in those situations. So we get our answers through factoring and changing. So the main thing to recognize here is if you have a double angle and another trig function, then you're going to need to use one of your formulas to solve it. If you just have the double angle, then you can solve it with the multi-revolution question technique that we've used in the past. So now we can go to example 4. The example 4 is on page 657. Can you see in example 4, you have a double angle. You have a sine 2x. We also have another trig function. So the very first thing we have to recognize is we cannot solve this as a multi-revolution question. We're going to have to use our identity. And right away we change the sine 2x to 2 sine x cos x minus cos squared x equals 0. With that half out in front, should I multiply the half by the 2, the sine x, and the cos x, or just multiply it once? I should distribute it? No. When this is only one term, right, we distribute if there's adding and subtracting in there. But since this is all multiplying, this half gets multiplied by this only once. And so we can just multiply a half by 2. What are we going to get? Just sine x cos x. Now, I have a cos squared, which means I could change my cos squared to 1 minus sine squared. Would that help me get a single trig function in this whole equation? No, I'd still have a cos. So whether I keep this as cos squared or change it to 1 minus sine squared, my equation would still have two different trig functions. So then I'm going to look at factoring it, and factoring it allows me to get a cos by itself, but inside the brackets I still have two functions. So here, this would mean cos x equals 0. How do you solve this? This means that sine x equals cos x. Okay, whoa, I know you guys are getting excited about solving that. Let's do the easy one first. Cos x equals 0. That's on our pi plates, pi over 2 and 3 pi over 2. Sine x equals cos x. How did you figure that out? How do you know pi over 4? They're both root 2 over 2 and root 2 over 2 at pi over 4. Is there any other place on our pi plate where that happens? 5 pi over 4. What happens at 5 pi over 4? They're both negative root 2 over 2 and negative root 2 over 2. So one way you can solve sine x equals cos x in this case is just thinking about your unit circle and knowing where they're equal to each other. Okay? In this case as well, another way that you could solve this, if I divide both sides by cos x, and I know we talked about not dividing just today, I would get sine x over cos x equals 1. What does sine x over cos x equal to? Tan x. So where is tan x equal to 1? Same answer as pi over 4 in quadrant 1 and 5 pi over 4 in quadrant 3. So why am I allowed to divide by cos x in this equation? Because cos x equals 0 is not a solution. For example, when cos x is 0 on this side, sine is going to be 1 or negative 1. Is 1 equal to 0? Last time I checked, it wasn't. Unless you do some really bad math. Okay? All right. To work on the homework, so from your textbook, I'm going to assign 12, 13, 14, and 15. And then on your identities, you know that identities worksheet that had all the happy faces? On the back side was a bunch of solving questions. Now on the back side, the ones I want you to solve are 8, 9, 11, 12, 14, 15. Yeah, I forgot 7 on purpose. 21, 27, 29, and 31. These numbers do not match. If you turn to the back and you're like, oh, you already circled the ones you want us to do. That's not true. The circled ones do not match with the ones that I've listed here. Okay? So 8, 9, 11, 12, 14, 15, 21, 27, 29, and 31 on the back side. These questions on the front side. And we have the rest of class to work on those.